Hello students, good morning to all. Welcome to online class. Myself Dr. Nazim Ahmed. In the previous video we discussed about molecular orbitals of butadiene and 1, 3, 5 hexatriene, and finally we discuss the symmetry properties of reactant and product orbitals. So various molecular orbitals of reactant and products are classified according to two independent symmetry operation. So one is the plane of symmetry, is denoted by small m, and another one is the axis of symmetry, is it not, which symbol is C2. So two things we discuss. One is the plane of symmetry M and axis of symmetry C2. For example, the symmetry properties of pi orbitals, bonding and anti-bonding of ethylene are classified in terms of whether they are symmetric or anti-symmetric with respect to both mirror plane and C2 axis. Okay, these two. So this is plane of symmetry and axis of symmetry. Plane of symmetry is symmetry, whereas the axis of symmetry is anti-symmetry. Similarly, this is for pi orbitals in bonding case, whereas the pi star in the case of anti-bonding is exactly opposite. So this is M, this is C2, that is axis of symmetry. So in the case of plane of symmetry it become anti-symmetric, whereas this C2 become symmetric. So this is the mirror plane. Okay, this figure shows that mirror plane M and C2 of ethene of pi molecular orbitals, is it not? Now the bonding orbital pi is symmetric with respect to mirror plane, which bisects the pi orbital. Now let us see. If I introduce a mirror which bisects, okay, which bisects the mirror the anti-symmetric A with respect to rotation of C2 axis. Rotation axis is C2. So what is this? This is the mirror plane, where this one is the mirror bisects the pi orbital possesses M symmetry. Okay. Now this is the pi, is it not? Now on the other hand, if you take this pi star anti-bonding orbital, okay, plane of symmetry, where this is the C2, okay, axis of symmetry. So what will happen? The rotation of the pi star orbital around the C2, around the axis C2, it results in a molecular orbital identical with the original. Therefore pi star possesses C2 symmetry. In the first case M symmetry, whereas here C2 symmetry. Okay, sorry. Next we pass on to, so this is the symmetric properties of reactant and product orbitals. Remember, plane of symmetry M and C2 is the axis of symmetry. Now based on that two electrocyclic reactions are very common. The interconversion of butadiene to cyclobutene and hexatriene to hexadiene. Okay, very important two electrocyclic reactions. Interconversion. Okay, interconversion of butadiene to cyclobutene and hexatriene to cyclohexadiene. Now let us, the symmetry of the orbitals of the butadiene of the cyclobutene can be described. Okay, so which we have to draw the 4 pi molecular orbitals of butadiene. 4 molecular orbitals of butadiene. Okay, in which we have to look at their symmetry properties. Okay, M and C2. Understand? Now let us, starting from psi 1, psi 2, psi 3, psi 4. If you draw, students, please make note of it. and you also draw side by side. This is psi 1, psi 2, psi 3, psi 4. Okay, now all are positive. %50 positive, in the case of psi 3 is alternate positive, negative, negative, positive. Here also alternate positive, negative. Okay, this is positive, this is negative. Okay, now look at the this is the 4 molecular orbitals of butadiene: psi 1, psi 2, psi 3, psi 4. So based on that, the symmetry is, what about the, with respect to mirror plane of symmetry is, this is symmetry. What will happen? This will become anti-symmetry, and this is plane of symmetry, it becomes symmetry, and this will become anti-symmetry. So what will happen at the same vice versa? In the case of, you are applying this C2 axis of symmetry, so it will become anti-symmetric, this will become symmetric, this will give anti-symmetric, and this will give symmetry. Okay, symmetry. Likewise, we will draw for the cyclobutene. We will draw for the cyclobutene 4 sigma and pi molecular orbitals of cyclobutene. Now here symmetry. What about the symmetry? M and C2. Okay. Now we will draw side by side. Sigma second level, pi in the third level, this is positive, this is negative, this is pi star, whereas both are positive, this is sigma star. So 4 pi and sigma molecular orbitals of cyclobutene. If we think about the symmetry of the first case is this is symmetry. In the case of these two are also symmetry, where these two are the anti-symmetry, and this is also anti-symmetry. Okay, yes, yes, A, A. Similarly, if we pass on to the axis of symmetry C2 axis with respect to, this is the mirror plane and the C2 axis. So this also gives symmetry only, is it not? Now this will give yes, yes, if anti-symmetry, and this will give symmetry, and this will give anti-symmetry. So this is the symmetry properties of butadiene and cyclobutene molecular orbitals. Okay, look at this, draw neatly. Next we pass on to correlation diagram. Correlation diagram for this rotatory of hexadiene to cyclohexadiene. Correlation diagram for this rotatory of hexadiene to cyclohexadiene, hexatriene, sorry, hexatriene to cyclohexadiene. In the previous class itself we discussed this rotatory and conrotatory concept. cyclohexadiene. This is the hexatriene. Now draw the energy levels. Psi1, Psi2, Psi3. Okay, this is the bonding region, whereas this one is the anti-bonding region, as you know very well. Okay, bonding and anti-bonding. So the here Psi4, Psi5 and Psi6. So if it is M symmetry maintained, okay, according to M symmetry, that is plane of symmetry based on M symmetry maintained. So in that case, what will happen? It will become symmetry. So in this side to become anti-symmetry. Similarly, symmetry, anti-symmetry, symmetry, anti-symmetry. Okay, if the plane of symmetry, it gives alternate symmetry, anti-symmetry, symmetry, anti-symmetry, symmetry, anti-symmetry. So it gives symmetry. Here also symmetry. Here we have anti-symmetry, symmetry, anti-symmetry, anti-symmetry. Okay. So yes, symmetry, symmetry, anti-symmetry, anti-symmetry. So this is sigma, this is phi1, this is phi2, this is phi3, this one is phi4, and this one is sigma star, sigma star. Now in the case of the correlation diagram, the correlation diagram for this rotative process indicates that the bonding orbitals of reactant correlates with the bonding orbitals of products, that is Psi1, Psi2, Psi3. Okay, Psi3, this is this rotatory, whereas sigma pi phi2 of cyclohexadiene. This is hexatriene, is it not? This is hexatriene. This process is thermally allowed. The process is thermally allowed. Whereas on the other hand, conrotatory process of C2 axis symmetry is maintained. The correlation diagram of this process indicates that it is thermally not allowed. It is Psi1, Psi2, Psi3 of hexatriene conrotatory system. Okay, sigma pi and pi 2 of cyclohexadiene, which is thermally not allowed. This will be thermally allowed. Okay, I repeat once again. In this process is thermally allowed. On the other hand, if we draw the same for maintaining this is M symmetry maintained, if it is C2 symmetry maintained, the same thing like that, what will happen? On some small changes, it will use the thermally not allowed. Okay, starting from here, symmetry, anti-symmetry, symmetry. So in that case, C2 symmetry, if you maintained, it becomes anti-symmetry, symmetries, anti-symmetry, exactly opposite. Okay, so with that I conclude. Next we pass on to sigmatropic rearrangement and Cope reaction. So today we discuss the symmetry properties of reactants and product. Based on that, we saw the entire conversion of butadiene to cyclobutene system, and find out the symmetry. Similarly, based on that, interconversion of butadiene to cyclobutene, and lastly we saw this reaction, thermally allowed and thermally not allowed. Okay, correlation diagram for this rotation of hexatriene to cyclohexadiene is thermally allowed, whereas in the case of conrotatory it is not allowed. Thank you.